I'll start the seminar now. It's my great pleasure to present Professor Lubotzky. He'll talk about stability, non-approximated groups, and the high-dimensional expanders. Thank you very much for accepting this invitation.
Okay. So let me don't say all the polite words and go right away to the talk. A group is called residually finite if for every G different than the identity in gamma, there exists an homomorphism from gamma to a finite group F such that the phi of G is not zero, is not one. Which means that the intersection of normal subgroups of finite index in gamma is trivial. Another way to think about it, that you can separate the points of the group gamma by finite images, which enables you to study gamma by sometimes reducing to problems about finite groups. Now, we all know that every finite group is embedded into the symmetric group by acting on itself by permutations from the left. So you can embed the finite group into the symmetric group, and therefore, equivalently, we can say that every element in that a group is residually finite if we can separate the points by homomorphism to the symmetric groups. And many groups are residually finite, more or less. Many groups that you meet in the street are residually finite, like linear groups are finitely generated linear groups are residually finite. The automorphism group of the free group is residually finite. Mapping class group is residually finite. But there are many groups which are not residually finite. For example, there are a simple group and even finitely generated simple groups. And of course, a simple group has no normal subgroups, and therefore it cannot be residually finite. Now, gamma is called sofic. Sofic, the story of sofic is a notion which basically invented by Gromov, and the study and the name was given by Benji Weiss. And a group is called sofic if there exist maps phi n from gamma to the symmetric group. Now look carefully at the definition. If it would be residually finite, then there are homomorphisms which separate the points of the of gamma. Now, what I claim that there are almost homomorphism, asymptotic homomorphism, namely, for every G and H in gamma, the limit when n goes to its infinity from the distance between phi n of GH and phi n of G times phi n of H, the limit of this distance is zero. Namely, they become more and more homomorphism when you go to infinity. For every G and H, for every pair GH separately, just this limit goes to zero. But we are interested now in such homomorphisms which are such almost homomorphism, or sometimes we call asymptotic homomorphism, which are honest homomorphism and not cheating. You can always say, okay, I will take every element to be very close to the identity, and then I will have a almost homomorphism, which is almost trivial. No, the question is, can we really separate the point of gamma by such almost homomorphism in such a way that for every non-trivial element of gamma, the distance between phi n of G is bounded away, between phi n of G and 1 is bounded away from 0. And all this here is with respect to the normalized Hamming distance on the symmetric group n. The normalized Hamming distance is simply the distance which says, which counts for two permutation on how many elements between 1 to n, they differ from each other. And normalized means divide this by n. So the distance is a number between 0 to 1. And with respect to this distance, we want that the group gamma is separated by almost homomorphism. Now it's a nice little exercise. Sorry, it's here the definition written. It's a nice little exercise to see that every residually finite is indeed sofic. And even more interesting exercise, which I will not stop because even if you are kind enough to give me more than 12 minutes, I don't want to take too much more. And then every amenable group is also sofic. So Gromov and Weiss' notion of sofic was a kind of a joint generalization of residually finite and amenable group. When they started that, it maybe was not such an important issue, but over the years it became extremely important problem, maybe one of the most outstanding problems in nowadays group theory is the question, are there non-sofic groups? Maybe all groups are sofic. We don't know that. That's a major open problem. Why this became such an important problem? Because there are nowadays, it was not like that when it was started, but nowadays there are good numbers of theorem which says if gamma is sofic, then blah, 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 blah. There is Kaplansky conjecture about some group algebras of group, which is still an open problem for general group, but for sofic group, it was proved. So you want to ask, maybe every group is sofic. Because there are so many theorems which says that everything is sofic and that sofic has such good properties, then I think people now incline to believe that not every group is sofic, but we don't have any proof of that. There are many suggestions for example or a counterexample, namely show a group which are not sofic. Well, take your favorite simple groups and finitely generate a simple group and ask, is it sofic? And this is not known. I want, you know, in mathematics, when we don't know to answer a question, then we generalize. So let's generalize. Let's, instead of looking at the symmetric group and the normalized Hamming matrix, let's take any sequence of groups, Gn, with a bi-invariant matrix Dn, and let's define exactly as sofic were defined, or to be honest, when sofic were defined for the first time, they were defined by different notions. It's kind of convenient for me to present them in the way I'm doing it now, in order to generalize it in this language. Anyway, if I take this family of G and Dn, I would say that gamma is G approximated with respect to this family G, if there exists phi n map from gamma to Gn, such that they are asymptotic homomorphism, namely this condition one here, that every map is eventual, that the maps phi n are eventually like or converging to homomorphisms, and the points of the group are separated by this family of maps. If you have these two properties with respect to G, you would say, we will say that the group gamma is G approximated. But now let me introduce the main examples that we will study. And the first one is Gn with a symmetric group and the normalized Hamming. This already we talked about, and that led being G approximated with respect to this family is exactly as being sofic. Now I want to give you a few more examples. The few more examples are going to be all of them. All the examples I will discuss today will be with the same group. The group will be the unitary group of complex number, n by n, a unitary group, but I will take different matrix. And you will see that this question is very sensitive to which matrix are taken. So we take the group Gn, and the matrix on Dn will be the distance between GH two unitary matrices will be the norm of G minus S. But what is the norm? Well, we can take many different norms. You know, there are many structure, kind of Banach space structures on the n by n matrices, complex matrices. All the norms I will talk today will be defined in the following way. For a matrix A in M and C, namely an n by n complex matrix, let's look at A star times A. A star times A, it's easy to see that it's a normal operator. That's the standard linear algebra. If it's a normal operator, it must be diagonal. Moreover, it is a positive normal operator, so all the eigenvalues are real, and all of them are non-negative, greater or equal 0. If this is the case, you can diagonalize the matrix and take its square root. So this square root, so A absolute value will be our notation to the square root of A star A. And no, this is not a number, this is a matrix. A absolute value is a matrix. This is the matrix of the square root of A star A. And now I'm going to define different norms on the, and therefore different matrix on the unitary group. If Gn is Un, the metric, the first one we'll talk about is the Hilbert-Schmidt metric, which is defined using the so-called Hilbert-Schmidt norm. What is the Hilbert-Schmidt norm of a matrix? You take the square root of, you take the trace of the absolute value of A, this absolute value of A square, namely absolute value of A square, you take the trace of it and you divide it by n and you take the square root of that. And this is called Hilbert-Schmidt norm. Now I have the definition now of being G-approximated, namely approximated with respect to these groups and this specific Hilbert-Schmidt matrix. It turns out that what we call now G-approximated is also a classical notion, which is called in the literature hyperlinear groups. And sometimes recently people started to call it Cohn's embeddable groups. The reason I think the hyperlinear groups is really not a good name, because when you say hyperlinear, what you hear that's something which is more than linear, right? But in fact, it's less than linear. Every linear group is hyperlinear, and not every hyperlinear group is linear. Now, it's known that every sofic group is hyperlinear, and it's a major open problem of Alan Cohn's, whether every group is hyperlinear. So you see, so the problem whether every group is sofic is kind of inside, if you want, this problem of whether every group is hyperlinear. By the way, there was a big breakthrough recently that the Cohn's embedding conjecture was disputed recently for algebras. It's still open for groups. For sister algebras, there are counterexamples. It's an amazing piece of work, very deep, which the negative answer came from quantum computation, believe it or not, from the theory of quantum computation. Those who are interested, a student of mine nowadays everything is in the internet, he runs a year-long kind of seminar course in Jerusalem about that. Let's take another example, and then you see how sensitive the issue is. The next example will replace the Hilbert-Schmidt matrix by the Frobenius matrix. What is the Frobenius matrix? Is nothing more than just taking exactly the same thing without the normalization. Take now, again, the same group, take the matrix now to be defined again using the norm, right? The distance between two matrices A and B is simply the norm of A minus B, but this time the norm is the so-called Frobenius norm, which is the square root of the trace of the absolute value square, instead of dividing by n. And now you would say what the groups which will be approximated by this will be called Frobenius approximated. Here I want to stress, now if you can, each one of you can think about it for a second, you see that in spite of the fact that the two norms look so much alike, the two questions are completely different. A group can be, in principle, we don't know, in principle can be approximated by one. Well, we know something. We'll see toward the end of the talk. It can be approximated using one definition, like Hilbert-Schmidt norm, and not approximated by Frobenius, or vice versa. Why? You see, the Hilbert-Schmidt is always less than the Frobenius, right? Because it's divided by 1 over n. Which means that if I have a family of almost asymptotic homomorphism with respect to the Frobenius, they are, of course, asymptotic homomorphism with respect to Hilbert-Schmidt because they are converging to 0 even faster. But maybe they are separate, the sequence separate the points of gamma with respect to Frobenius, but does not separate with respect to Hilbert-Schmidt, because Hilbert-Schmidt will take you to 0, while the Frobenius will keep you away from 0. And also think about the converse. In the other direction, it will work in the opposite direction. So we cannot deduce from one matrix to another. Each one is a different problem. So we have like two open problems here. Are there non-Hilbert-Schmidt approximated groups? Are there non-Frobenius groups? The next example will show you that not only that we have two different problems, we have uncountably many problems, different problems, because for every p, now p is not a prime as we algebraists like, but p is like the analysts like to say. P is any number between 1 to infinity. We can take this is called the Schachten P norm. We take the absolute value of A to the P power, we take the trace of it, and then we take 1 over P. If you think about it, it's more or less like the LP norms of the eigenvalues. So I can talk now about P-approximated groups. So for every P, it's a different problem. If I have two P and Q, even if the matrix Q is always less than the matrix P, I cannot deduce from one another. So the question is a new question for every P. Do you have non-P approximated groups? And there is also the case of P equal infinity, which is called the operator norm. And sometimes this is thought, if you think about it, in some sense, is the limit when P goes to infinity. The operator norm is the standard norm on the matrices, which says that the norm of a matrix is the maximum or the supremum, the maximum of the A of V, of the standard norm of the vector A of V, the V runs of the vector of norm 1 in the complex number. And operator approximated groups are called in the literature for some reason MF groups. And it's a major long-standing problem going back to Chiffre, originated in C-star algebras theory, whether every group is operator approximated. I think Kirchberg even conjectured that this is the case, but I think nowadays when people think about these problems together, they don't believe that this is the case, but nobody knows. Okay, the good news of today that we have a solution to some of these problems now. And this is the main results that I want to talk about today. The first theorem, which in a way that was the breakthrough which enabled all the rest, is a joint work with Marcus de Chiffre, Lev Glebsky from Mexico, and Andreas Thom from Germany. And Marcus is a student, ex-student of Thom, and was part of his thesis. And the theorem says there exists finitely generated, even finitely presented, non-Frobenius approximated groups. So if we look at the Frobenius norm rather than in the Hilbert-Schmidt norm, we can solve the problem. And present a group which cannot be approximated. It does not solve, let me stress, the Hilbert-Schmidt case, which is the famous Alan Korn's open problem, whether every group is hyperlinear, because it's a different norm. It's the one without the normalization. To be honest, if you would ask me 3 years ago about these two problems, which one of them is more difficult, who knows? I guess if I would not have only 12 minutes, then I would say a little bit more, or I even take a vote among the audience what they think, which of the two is. It's not clear why we can solve this and not the other. But I hope that by the end of the talk, it will be clear. Shortly after that, I wrote a paper which is our Oppenheim based on that method, and we prove, in fact, even stronger results that solve the problem for every p between 1 and infinity, and even in a strong sense, namely, there exists a finitely presented group which is not p-approximated for any p between 1 and infinity, for every p. You don't have to, for every p, to choose a different group. There is one which is not approximated for any of them. So if 3 minutes ago we had uncountably many open problems, we are left only with 4. Unfortunately, we left with the 4 most important ones. I would even, I have to admit, at least for the first 3, I would trade the papers on which solve for this infinitely many p's with one paper that would solve one of these 3 major problems, or a long-standing problem. But part of the contribution, I think, of our work is really to understand the difference with the problem. Why it turns out that these problems are more difficult than the one we solved? Because really, when you look at it the first time, you don't see why. And I will try to explain. Okay, for the proof, from now on, I basically start a new talk, a new 12-minute talk. On the subject of stability, which is of interest by its own. And I have to admit that at least I started to study this type of problem because of interest in stability, and my interest in stability came in some sense from computer science, from something called property testing in computer science. But I don't know if I will say much about that aspect. So let me explain the notion of stability. And even if you lost me before, in some sense I'm starting a new talk. And eventually, of course, they will be connected. Let G be equal, again, as before, is a family of groups Gn, and with matrix, each one of them comes with a matrix Dn. We have a groups with matrix, and gamma is any group, any, say, finitely generated group. We say that gamma is G stable if whenever we have asymptotic homomorphisms as before from gamma to Gn, they are not really something new. You know, you can always take a true homomorphism and permute them a little bit, you know, just change them a little bit. Then there exists homomorphism. So we say that gamma is stable with respect to the family G if every such family is really just a small perturbation of honest homomorphism. Namely, there exist honest homomorphisms from gamma to Gn, such that for every G in gamma, the distance between the true homomorphism and our almost homomorphism goes to 0, which means that it's not really an honest, almost asymptotic homomorphism. They are really homomorphisms. There is a connection to computer science. If you just think about it for a second, I will. Those who are familiar with the topic of property testing, which is a very hot subject in computer science, maybe the deepest one in the current theoretical computer science, and even with down-to-earth application, you can think of it as testability of equations. Why? You take if gamma is a presentation by generators X and relations R, and you take G to be, say, the example of the symmetric matrices, then what does it mean in homomorphism, and what does it mean almost homomorphism? Homomorphism means a map from X to the group Gn such that all the relations are satisfied. The relations are like equations. Right? So homomorphism is a true equation, and almost homomorphism means that the equation is almost satisfied. The equations are almost satisfied, and that's completely equivalent. For example, here is a non-trivial theorem. The group Z2 is stable, and that's theorem. And this means that if you take two permutations, now this is a down-to-earth theorem that you can explain every kid. If you take two permutations which almost commute with each other, when n is very large, you can change them a bit in a small percentage of the indexes to make them truly commute. But it's a non-trivial theorem. I don't know any simple proof for that. Any kind of direct, this is a completely different direction that we work, and you'll have to invite me once again, and then I'll come on time. And then I can tell you it related to IRS, invariant random subgroups in one way, where there are other proofs, but none of them is easy. And that's kind of, you feel that there is a kind of a computer science issue here about what is called testability of equations. Okay, but I will not elaborate on this, but I will explain now what's the connection between stability and approximated. And here is a little proposition, observation, going back to Lev Glebsky, which I mentioned before, in a short paper with Riviera, which appeared already 15 years ago in the Taiwanese Journal of Mathematics. And they made the following excellent observation. They said that if you take G, like the symmetric group or the unitary group as above, doesn't matter what the exact norm, and gamma finitely generated, then if gamma is G approximated, as well as G stable, then it must be residually finite. Okay, every talk should contain a proof. So let me give a proof for that. Gamma is G approximated. What does it mean? It means that there is a sequence of asymptotic homomorphisms, almost homomorphism, Pn, from gamma to Gn, which separate the point, right? But first of all, these are asymptotic homomorphism. But if gamma is also G stable, it means that nearby you can replace each one of these phi-n, you can replace by psi-n, by a true homomorphism. And if you think about it for a second, if psi-n, if the phi-n's are separating, then psi-n are also separating. So I can separate the points of gamma by homomorphism to Gn. If Gn is the symmetric group, we finish. If it's Un, then the real meaning is that gamma is separated by homomorphism to linear groups, but gamma is finitely generated, so the images are also finitely generated. We know that every finitely generated linear group is residually finite. This goes back to Maltsev. I mentioned it in the first slide, and you know, this is like a play of Chekhov. If you see a pistol in the first slide, it should appear somewhere later. We said that linear groups are residually finite. So if they are residually finite, I can separate now the points of the image by finite groups. So if I can separate the point of gamma by homomorphism to this psi n of gamma, and I can separate the points of psi and gamma by finite homomorphism to finite group, I can separate the point of gamma by homomorphism to finite group, and therefore gamma is residually finite. Okay, this is a very simple proposition, but it has a great corollary, which is just writing it in a different order, right? If gamma is finitely generated, G stable, and not residually finite, then it is not G approximated, because G stable and G approximated should be residually finite, right? Okay, so this gives a suggestion where to look for non-G approximated group. If you want a non-sofic group, just find a group which is stable and not residually finite. The problem is that this is much easier to say than to do. And up to recently, there are really, in a way, dramatic developments in this area in various directions. Today, I will show you one of the direction, but there have been several pretty dramatic developments in this area in the last 2-3 years. That suddenly we have some technique. Till a few years ago, very little was known about technique to prove stability. If you think about it, it's highly non-trivial, even for the challenge I give you, just to show that this cos Z is stable. This, by the way, a problem which was studied by the physicists long ago. In their language is basically the question: if two matrices are almost commute, can you deform a little bit to commute? And this is kind of the Heisenberg uncertainty principle and things like that. So it was a question with motivation. But except of this commutation, if you take a more involved equations, nobody knew how to handle the stability, only in the negative somehow, but no positive results. And now we need positive results, right? So the G is stable. So how do you prove stability or instability? And in a way, the paper with Marcus de Chiffre and Glebsky and Andreas Thom, the main breakthrough was really that we had suddenly a technique, a method to prove stability. And the method, if you look at it at first sight, you don't understand where it comes from. I will tell you the secret toward the end of the talk. And here is the theorem. Assume gamma is finitely generated, and assume that H2, that the second cohomology group of gamma with coefficients in V are always 0. It's always equal to 0 for every unitary representation of gamma on any Hilbert space V. I guess you wonder where H2 comes to the game, where cohomology comes into the game. We were talking about down-to-earth problem, and suddenly that I will come to that later. I will say something. Then gamma is stable with respect to the Frobenius norm. Okay? If the cohomology of gamma always vanish, I prefer at that point not to explain this theorem. Let me take this for a minute as a black box. We'll show how the main theorem follows from that. There is also a nice story there, and then I'll come back and I will explain the main point of this theorem. Okay, so what do we need now? Now, you remember our goal is to get non-approximated groups, not G-approximated groups. So we want to get a group which is G-stable and not residually finite. Now, this theorem tells us that G-stability, at least for the case of UN and the Frobenius norm, will be obtained if I would have vanishing of cohomology. So I have to look for groups with vanishing of the cohomology, H2 always vanish, and the non-residually finite. Some of you may remember that vanishing of H1 gamma V for exactly that, H1 gamma V equals 0 for every unitary representation of gamma on any Hilbert space V is exactly equivalent to Kazhdan property T. The group gamma is Kazhdan property T, if and only if it has this vanishing theorem. And this is a little hint, maybe where to look for H2. Those of you familiar with Kazhdan property T, you know the connection with expanders. So now we will have a connection with I-dimensional expanders in a minute. And this is the so-called Garland theory. Or if you want local to global expanders. I will just basically quote the theorem of Garland. Garland actually proved it only for finite dimensional spaces, and it was extended by Bolman and Svetkovsky to Hilbert spaces. And even if you don't understand some of the words here, it doesn't matter. I will give concrete examples. But the general theorem is more or less the following. Let G be a simple algebraic group over the p-adic numbers. Let's say SLN QP, SLN over the p-adic number, or SP over the p-adic number, or whatever. Of rank R. What is rank? It doesn't matter. For SLN, the rank is n minus 1. But what is important for us, little bit important, that the rank, every such simple group acts on the so-called Bruhat-Tits building associated with G. Those of you who are familiar with the theory of the real numbers know that when you start with a simple real Lie group like SL2R, SLNR, you divide it with a maximal compact subgroup, you get the so-called symmetric space. Bruhat-Tits developed such a theory over the p-adic numbers, and there G mod K is not a Riemannian manifold, but rather is a discrete object, is an infinite simplicial complex, a contractible simplicial complex nowadays called the Bruhat-Tits building of G, whose dimension is equal to the rank of R. Now, Garland proved that if the rank is at least 2, and if gamma is a subgroup of G, a co-compact lattice, which means that it's a discrete group so that G mod gamma is co-compact, or equivalently, it means that when gamma act on the Bruhat-Tits building B, the quotient is a finite simplicial complex of dimension R. Anyway, this is just introduction. What the theorem said, the theorem says that if the prime P is large enough, then all the cohomology group vanish. HI, all of them vanish for every I between 1 and less than R. So this gives us a large source of examples of group which H2 vanish, right? That's exactly what we need. We need H2 vanish for every unitary representation on any Hilbert space. And okay, if we take the rank to be at least 3, and then we get H2 vanish, and these groups now, wonderful. We have many groups which are stable. What's the problem? That all of them are residually finite, because each one of these gamma is a finitely generated group in a linear group, and so it is residually finite, but we want to get non-residually finite stable groups. What we should do? Well, usually it's much better to be young than old. The old people have one little advantage. They remember things from many years ago, and some of you maybe knew about this little theorem of Deligne. Deligne in the late 70s constructed the following non-residually finite. To be honest, I never really understood why he cared, even though later on it became a fairly important result, which, anyway, let's say first of all what he proved. He took an arithmetic lattice in a real group, the SP2GR, gamma, and he showed that there exists a finite extension of it with finite kernel. There is such an exact sequence. With Z is finite, gamma is an arithmetic group over there, and gamma tilde is not residually finite. So it's not residually finite on the nodes because gamma is residually finite. So the intersection of the finite index suburb of gamma tilde is not trivial, but it's just the group Z, which is a finite group. It's almost residually finite, but not residually finite. Just to, if may ring a bell to some of you, later on Raghunathan showed how to construct examples like that which are co-compact, and later on this became famous by the work of Toledo, who used it to get to solve a problem in algebraic geometry, showing that the fundamental group pi1 of some projective varieties need not be residually finite. So anyway, that's the little history. Now what we did, we took the construction of Deligne and imitated it over the p-adic numbers. Namely, we started with such a group gamma, with a lattice, which is an arithmetic group over the p-adic number. One of those groups for which the Deligne theorem is valid for. And then we took this little central extension, which is and more or less the theorem of Deligne, the proof of Deligne, the theorem could apply here. Well, along the way, we have to use results which were not known at the time of Deligne. The congruence suburb property, which meanwhile was proved for this by Rapinchuk. So there is, we are kind of lying on the shoulders on a lot of other people. Anyway, we were able to imitate this. Here I want to give a credit to Dave Whitty Morris. Some of you may know. Just to show that that it's helpful to be kind. I had a lot of difficulties to read the paper of Deligne and to understand this proof, and not only because it was in French. And luckily, I found on the web that Dave Morris gave some few years ago. He gave a talk somewhere, or presented this paper of Deligne, and he put his talk on the web, and that was very helpful because the way he presented the proof I could understand, and then it was not so difficult to imitate it to the p-adic number. Okay, so now you can see, you see what we know. We know by Garland that our p-adic example, the H2 always vanish. This has a finite kernel, and then there are standard spectral techniques to show that the cohomology of H of gamma tilde also vanish. So this gamma tilde for the p-adic numbers, we have to take the symplectic group of the p-adic, we take gamma arithmetic co-compact, we do this imitation of the Deligne construction, and now this gamma tilde is vanishing cohomology, therefore stable, and therefore not approximated. Now I owe you two things. the second theorem about the LP was basically on the same idea, but doing it, extending the criterion. Instead of Hilbert spaces, one should know the vanishing to a more general Banach spaces. So the work with Isar Oppenheim, was exactly an expert on this Garland theory for Banach spaces. We worked out the extension, and we get here, and there is a little group theoretical argument that I won't get in. I won't do it. Instead, I will reveal to you the secret in 2 slides, basically, very shortly, what H2 has to do with the subject. And I have to tell you that, again, it came to us, it's not like we really understood it right away. We worked, we tried various things, and suddenly we saw that we are getting cocycles, and eventually we understood in a conceptual way. And I want to save you the suffer, and I will show you the conceptual way to understand why H2, why cohomology is relevant to this subject. Okay, so let phi n be a sequence of gamma, of maps from gamma to UNC, asymptotic homomorphism as before. Let U be the direct product over all n of all these groups UN. And let U bar be the topological ultra product of UN. If you are familiar with this language of ultra product for model theory, fine. If you are not familiar, just think about it. You can a little bit cheat yourself, that's fine. That U bar is U mod K, where K is the sequence of, is all the sequences of Gn in UN whose limit is 0. What we have to take is the limit with respect to the ultra filter. But if you're not familiar with it, that doesn't really matter. Think for a second, you take the limit with, you divide by the sequence of all elements which converge to the identities. The distance between them to the identity converges to 0, namely they converge to the identity. This trick of this language does for you something fantastic. Why? Because you see, think about it. We started with a map of almost homomorphisms from gamma to UN. This is like a family of almost homomorphism. We can think of it as one map, diagonal map, like from gamma to the direct product, from gamma to U. And this is not an homomorphism. But if I divide by K, what is K? K are all the sequences which are going to 0, which are going to the identity, which means that after dividing by K, this one map from gamma to the product, this diagonal, becomes an homomorphism, because you see, you remember the distance between phi n of GH to phi n G, phi n H goes to 1, which means that 1 times the other, the distance goes to 0, which means that the difference between them goes to 1, which means that modulo that these are true homomorphism. So we are back in the category of homomorphism that we know how to work with. You see, we don't know how to work with almost homomorphism. What is a kernel of homomorphism? Nobody understands something like that. But with homomorphism, we have already, I don't know, 300 years of experience to work with groups and homomorphism, or maybe less, but I don't know. Moreover, let me show you in the language of groups of homomorphism, what does it mean to be stable? Gamma, if you think about it, that's very simple to see that gamma is stable if and only if every such phi, you see, phi is the map which starts like from gamma to U and then from U to U mod K. Every such phi from gamma to U mod K can be lifted up to a true homomorphism from gamma to U. So it becomes a lifting problem. The stability is nothing more than a lifting problem of homomorphism from gamma to U mod K to U. Now, this is a very difficult lifting problem because K is an orbital group. And not only that its topology is orbital, but even as a group, it's a very non-commutative group, very difficult to understand it. For example, if you think about it, K contains, it's a subgroup of the direct product, but it contains the direct sum. So it's not easy to understand what is K. But the magic is that it's a simple lemma, which because I don't have time, I won't show it, because those people who have experience with congruent subgroups know, I saw in the audience, I managed to see, that if you look at the congruent subgroup mod P, and you look at it mod P squared, the quotient is a billion. There is like a magic there. The magic here is if the norm we are working with is submultiplicative, which is the case for all these P, but it's not true for the Hilbert-Schmidt. The Hilbert-Schmidt is not submultiplicative. Submultiplicative means that the norm of A times B is less or equal norm of A, norm of P. For the Frobenius, it's true. For LP, it's true. But for Hilbert-Schmidt, we normalize. You remember this little normalization destroyed the submultiplicativity. So we cannot apply what I'm going to say now for that, but I can apply it for the other. Then we can approximate K by a sequence of abelian extensions. We can do this lifting to K step by step, where each step is an abelian extension of the previous one. Now, by Hilbert spaces, if P equal 2, and if you do it for the other P's, you have to do Banach spaces. That's why I explain you that in the original work with Lev and Marcus and Andreas, we work with Hilbert spaces. With Izar, we had to go to Banach spaces. But anyway, you see that H2 is the machinery, is the right machinery, because H2 is exactly the machinery for such lifting problem. If you know basic cohomology theory, that calls to H2 to come into the game. Okay, that's all, and 58 minutes. It was the longest 12 minutes talk that I ever gave, 58 minutes.
Okay, let's see the microphone to, thanks for Professor. Now are some questions, comments?
I have question, have comment actually.
Yeah.
Well, I want to come back to this Deligne example, which probably tells us that we're in the same club of old people. I sort of wanted to ask why actually, because I have this, it is somehow connected to goodness of a group. You know that good groups, it is when cohomology of this and the profinite completion coincide.
Yeah, I know.
Here actually to coincide H2 cohomology.
Yeah.
And morally, every arithmetic group with congruent subgroup problem should have property that H2 doesn't coincide with the H2 of the profinite completion.
Right.
So it means that actually not only for this example of Deligne, but actually for practically all arithmetic group with congruent subgroup problem, this should be an example.
That's actually, it will be a wonderful topic to do. I have the feeling that you are right, or at least almost right, because if you say for every, I'm not completely sure, but I'm sure.
No, I said morally for every.
Morally, yeah. Actually, I do believe that you are right. I do believe there is a good chance that, but you see, over the real groups. So let's be a bit careful here. because for real groups, I don't know. I'm not saying it's not true. I'm just saying that I don't know vanishing of H2 for all unitary.
Mm-hmm.
You see, there is a lot of that on that in the book of Borel and Wallach, but that book is very difficult to read, and somehow I couldn't figure out if you really have the vanishing results that we need. I have to admit that it was more convenient for me to go to the Garland theory because that's related to high-dimensional expander, Ramanujan complexes. Some of you maybe heard me talking about this subject in the last couple of years. And so even though it sounds like combinatorics, everything is related. It's not different. But I think I think morally you are right. Yeah, I think probably there are many more examples like that. Yes.
Some other questions?
I have a simple question, actually. Okay, according to the last part of your argument that you gave, so submultiplicativity holds also for p equal to 1.
Yeah.
So what was the problem in the case of p equal to 1?
Yeah, okay. I try to hide this. You're right. It holds for p equal 1, and it also p equal infinity.
Yes.
Which is even more.
Yes. But you are
completely right. You are completely right. And all what I said is true for them, except of the vanishing of the cohomology over Banach spaces. The Garland theory can be extended for all p greater than 1 and less than infinity. In fact, there is something even more delicate there. If you remember in the Garland theorem, the theorem, at least that's the way I wrote it, was not saying that it's true for every p. It said that it's true for every p large enough. Now, this p is the prime p. The two p's play a different role, right?
Yeah.
Now, if you take p of LP and you want to prove like this theorem, you have each time to take bigger p here.
Mm-hmm.
So in infinity, so you have to say for every p of the LP, it's true for every p much larger than that, and the much larger is larger and larger. So the p infinity, that's the moral story. But the problem is that there is a delicate issue here. I don't think it's true that this group, in fact, now I know to prove it. Sorry, when we did it, I didn't know. Now I even know to prove that these lattices of Garland, at least I know to prove for some of them, are not stable with respect to L infinity. Mm-hmm. The operator no. I don't know it for L1. So you see, the problem is that the issue of the abelian extension is correct, but the vanishing is not. But that was, you caught me on a delicate issue, yeah.
Some other question? I have maybe a stupid question, but I'd like to understand a little bit more. How the connection of the notion of sofic and the G-approximated or hyperlinear group are related with the notion of the group that admits a matrix model in the sense of the logic.
In which group? The group of what?
The group that admits a matrix module.
Now, what is matrix model? Matrix model means that they satisfy the same equations like matrices, something like that. What? Sorry for my ignorance, but I forgot what. I think I heard that. What is matrix model?
Model.
Yeah, what's the definition?
They have the same first theory of the.
The same first theory of a linear group.
Yes.
It's a good question. I don't see a direct connection. I worked even about that. Recently, I wrote a paper on first order, a theory of exactly this group, arithmetic lattices. It's just been published recently. But just a second. It didn't occur to me. Maybe it's a good suggestion. I have to think about it because I probably had to think about it anyway, but for some reason I didn't. But I don't see. There is, in the language of weakly sofic, there is, Glebsky wrote some papers on that, not exactly on the first order language, but on solution of equation. He showed that, I think it's somehow if I remember, there is something which is called weak sofic, which is equivalent that every equation that can be solved in a finite groups can be solved in an overgroup of the given group gamma, I think. Okay, I mean, I don't have a clear answer, but it's a good question that one should really try to, at least to understand if there is a connection or not, and if yes, to what extent. I'm sure they're not equivalent, but I have the feeling that there might be some connection, yeah.
And how about that you said that testing of equation there are applications in the computer science. Could you give me some taste of this? Is it easy to say something about it?
Actually, yes. You see, what does it mean? Stability. Go to the example that I hinted about. One example. The example I hinted about was this story. You look at to say that the group Z cross Z is stable is amount to say that if you take the two permutation which almost commute, then they nearby two permutation which commute. What does it mean that they almost commute? If you think about it for a second, to be almost commute in this normalized Hamming matrix mean that if somebody will choose I between 1 to n randomly, then with I probability sigma of tau of I is equal to tau sigma of I. Okay, right? That's, if you think about it, that's exactly the meaning, that with very high probability, say 99%, that will hold. And the question is, can you change little with the permutation that it will hold 100 times? Now, property testing is the subject in computer science which try to see, can you check a property of an object? The most important open problem there is about error correcting codes. You have a long word inside some code, and you want to check whether it's really inside the code or at least very close to it so that you can correct it to the code. But you want to read only very few bits, like the length of the code is 200,000 and you are allowed to read only 50 bits. Can you decide about that? Now, that's called locally testability there. Now here, I think about the commuting matrices as your code. All the pair the commuting permutation, all the pairs of permutation in Sn cross Sn which commute with each other, this is a subset, this is your code. Now I give you two permutations and I want you to check, are they nearby the code or not? Then you said, okay, I don't have to read the full permutation. I just take 7 random I, and I will check ABI equal BAI. If it holds for all 7 of them, I know that with very high probability, they are nearby commuting, namely they are nearby the code. So this way of thinking is really that the problems we study here are really, if you want, sub-problems in the theory of property testing. In fact, just recently I wrote a paper with 2 young guys. It's just, we put it on the archive a few weeks ago on exactly explaining the connection between group theory and these testability questions in computer science. It's Oren Becker and Jonathan Moseyev.
Okay, thank you. Some other question? If not, let's thank again Professor Alex Lubotzky.
Thank you very much. And again, I apologize.
Let's